All right, everybody, it's 6:10. Welcome back. Before I get started, I want to make sure that I put a few announcements on the canvas, and I wanted to make sure that you were able to see them. Also, are you getting notifications about them, or is this the first time you're hearing about it?
It's the first time I'm hearing of it, but I can see him.
Okay. All right. I'll probably have to fix it on my end. So yeah, there's a all right, someone's getting the notifications. So it took YouTube a long time to process the video file that I posted this morning, but it was I think it was up around 11:30. So I'll try to get that done a little earlier going forward, but they should be there. I'm gonna go ahead and post my link to my channel in the chat. So yeah, you can subscribe to that, or I'll also be posting links to the canvas every day. So either way is fine. Any questions about anything before we get started? All right, I think 3 or 4 of you should have grades on your first quiz. I'll finish the rest of them tonight. I'll get those in as quick as I can. The solution to or my solution, a potential solution, is available on Canvas now if you want to look at it at some point. All right, let's get going. All right, so yesterday we spent the last half a class or so on areas. Now I want to talk about volumes. So, and you can't talk about volumes without having a pretty good understanding of area. So just kind of refresh. Basically, if I want to find the area under this curve, between the curve and the x-axis, this blue shaded area, just a reminder, really all I'm doing with an integral, it's really just taking this, strange area that has, there's no geometric name for whatever this shape is. Just like there won't be some canned formula you can just rely on for most of these areas that we're going to come up with. So really what you're doing is you're breaking this thing down into, let's call this point, x plus delta x. And really all I'm doing is taking this curve and making a bunch of rectangles out of it. So this is essentially what we did last night. Basically, I'm splitting up that area into many smaller rectangles. Rectangles are really simple to find the area of, so just take the area of all those, add them all up, and that's my area. So area is a two-dimensional measurement. Now we're going to extend this into the third dimension. So basically, what's going to happen if I take this rectangle, and now we're going to make what's called a solid of revolution. And it is called that because you're going to start with the area, like this blue shaded area here, and then I'm going to revolve that area around some line, some straight line. So most of the things you're going to see are going to be the y-axis or the x-axis, but really it could be any straight line. We're going to limit ourselves to horizontal and vertical lines. So eventually I want to find that volume by wrapping this entire area around this one. We're going to do the x-axis, wrap it around the x-axis to make a solid three-dimensional figure and find that volume. But just like with area, we're going to do very simple shapes and just add all these things together. So just to highlight this, I'm revolving around the x-axis. So if I were to take this rectangle, and I'm going to try to represent this in 2 dimensions the best I can. If I were to revolve this around the x-axis, what shape is this going to make?
A circle?
So a circle is still, I mean, yeah, if you were to kind of look at it to the side, you would see this flat circle, right? But let's expand that a little more, because a circle is really 2-dimensional. If I take that rectangle and spin it around the x-axis, I'm going to have something that exists in 3 dimensions. So yes, it's going to have a circular cross section, but it does have a thickness to it. So what is that shape really?
A cylinder.
That's going to be a cylinder. So kind of the analogous thing we're looking at here is, you know, when we were dealing with areas, we were looking at rectangles. Basically, for any area, I can use integrals and just take any arbitrary shape and basically partition it into a bunch of rectangles. The analogous idea for volume is another shape that's relatively simple that I can deal with is cylinders. So that's essentially what we're going to be doing with volumes in this way. So there's my bad drawing. Let's look at a better one. So basically, let's take another slice here, except now when I take a slice of in some x interval, it's not really, I mean, I'm going to start with a rectangle because I have to, but you know, my kind of intermediate product here is not going to be a rectangle. It's going to be this 3-dimensional thing that we just talked about. And that's going to be a cylinder. So basically, to find this volume, what I'm doing is, and I'm going to represent this again as a limiting sum. So as n goes towards infinity, I am adding up volumes of cylinders. So for now, I'll just represent this as VCYL. Okay, so let me go ahead and pause there. Are we okay with the rationale of what I'm doing? Are we, because it's going to be really important for not only today, but tomorrow. We're going to talk about volume for quite a while. Are we okay with the rationale for why cylinders are going to be important? Pretty much the entire time we're talking about volume. If you're not, please ask me a question. Go ahead and stop me. This is a pretty crucial thing to grasp before we go too much further. All right. So if we're going to be adding up all these volumes of cylinders, we need to think about how to find the volume of a single cylinder. So how do we find the volume of a cylinder? Or if we don't remember, so a cylinder is a specific type of prism. And what I mean by prism is, you know, a prism by definition is any 3-dimensional shape that no matter where I were to take a cross section of it, it would look the same. So a cylinder, no matter where you take a cross section of it, you're going to get a circle, and no matter where you slice it, you're going to get the same size of a circle, same radius. So it's a prism. Do we remember how to find volumes of?
Pi.
Did I hear pi?
Sorry, pi r squared h.
So pi times radius squared height. And just because I was starting to build up there, the volume of any prism is essentially equal to the area of the base times its height. So, and if we try to look for parallels between these two ideas here, obviously we see the height. What shape is the base of this cylinder?
Well, wouldn't it just be a circle?
Yeah, it's just a circle, which is hopefully it makes sense that the volume of cylinder is pi r squared h. Pi r squared is the area of a circle, and that's what shape these bases are. So basically, when we're gonna be doing an integral here, and really all we're gonna be doing is adding up all these little subvolumes. And all those little subvolumes are going to be cylinders, so they're all going to be represented by this pi r squared h because we're dealing with cylinders. So now we really need to know how to represent r and h in terms of our independent variable. So we're going around the x-axis. So let's start building up this integral. So the volume of this is going to be, we're going to integrate from a to b, whatever those limits are. And we're looking at pi r squared h. So now really what we want to do is we want to represent the radius and the height of our cylinder in terms of this function itself. So like I said, I mean, whether or not you've noticed it so far, our calculus right now is limited to a single variable. So we want this thing, and I'm gonna go ahead and make this more explicit. We need this to be in terms of x. So that's our end goal. We can kind of work up to that, as gradually as we need to, but that's our goal. So the radius. Did someone say record? I think I am. Am I not?
I think you are.
I think I am. Okay, good. So back to the radius. Any ideas for how I would express the radius in terms of the function or in terms of the variables x and y? I'm going to go ahead and draw at least one more strip in here just to, this width is going to be dx.
The value of the function.
Yeah, so the radius is just going to come from the value of the function because, just think really basic. What is, actually, I'll just ask the room here. What does the word radius mean?
Halfway on the edge of the circle, or like from the edge of the circle to the center.
Right. So yeah, that's exactly it. So from the edge of this the circle to the center. Let's go back. So the center of our circles is always going to be the x-axis. The circumference of the circle, the edge of the circle, is always going to be given by whatever the value of this function is. So our first move here is we can swap out r with f of x, so f of x squared. All right, last thing we have to take care of is the height. So all these little cylinders I'm going to make, what's their height going to be given by?
The DX.
Going to be the DX, right? So these cylinders are kind of, for this particular example, the cylinders are kind of lying down their side. So really when you're looking at a thickness, like a horizontal thickness. So really our integral is going to look like this. And you're going to see a few different methods for how we integrate to find this volume. This one's called the disk method. Hopefully it's clear why it has that name, even though you haven't seen what the alternative approaches are. But really what I'm doing with this area is I'm cutting, or this volume is I'm cutting this volume into many cylindrical disks and finding the volumes of each one. So any questions about where this thing comes from here? It's gonna be really crucial going forward. One thing I will point out before we go any further, and this is not an accident, but think about the way we did area. Area is a two-dimensional concept. And when we integrate, really what we're doing when we integrate is we're integrating a bunch of lengths. And because up above here, I'll write area is equal to basically the integral from over some interval of the function times dx. And really f of x, that's a length. That's a one-dimensional height. Basically, whatever the value of the function is I just want to know how far is that from, in this case, this would be the x-axis. So area is a two-dimensional measurement, and to find that area, I integrate on a one-dimensional measurement. Volume is a three-dimensional concept, and to get that volume, I am integrating on, really, this is pi r squared. That's an area. So it's not a coincidence that basically the integral is going to be of one fewer dimension than the thing you're actually trying to accumulate and find. So any questions on where we found this this volume integral before we go any further? We're going to be using this thing quite a bit. All right, let's look at an example. So first thing I want to look at here is we're just going to do a very simple function. I'm going to take this area here, and I want to revolve this around the x-axis. So I'm going to take a rectangle here. Revolving around the x-axis. Hopefully you're okay with the idea that this is going to make a cylinder that I can't quite complete because this is a little bit too tall. So if I were to take this whole area and revolve this around the x-axis, what would that overall shape be? Would that be something familiar?
It's a cylinder, right?
It's gonna be a cylinder. So really, in other words, I don't really need an integral to make this happen. I have this, you know, this familiar formula for finding the area of a cylinder or volume of a cylinder. So we'll use that to check ourselves, but let's also set up an integral, just get in the habit of doing that. So basically we're going to be adding up adding up volumes of little cylinders here. So let's just start kind of building this up. These limits of integration. So one thing I should point out explicitly, I don't know if I said this, this is going to be all as x is my independent variable. And for this method, that's required. Kind of give you a taste of what we're looking at in the future here. If I were to take this vertical strip here and revolve it around the y-axis, it would not make a solid cylindrical disc like this whole method depends on. So one requirement we have for the disc method is that, and I'll write this out really explicitly, axis of rotation is, what's the right way to say this? Maybe I'll take some suggestions from you. What I want to say is this, or here's what I want to try to generalize. So in this case, the x-axis is going to be the axis of rotation. So I want my intervals to be dx. So let's try this. Independent variable is, I'm going to say not equal to axis rotation, but parallel to. Parallel to axis of rotation. And the reason I say that is because we're going to do some examples later today where, you know, right now I want to revolve this around the x-axis, but I also could revolve it around like y equals 2 or y equals -1, which those are also going to be horizontal lines. But for now, let's just get started with the x-axis. So basically A and B are going to be x values. The radius and the height, we need to express those in terms of x. So first thing, let's do this is, what interval am I going to be integrating on? So what does it make sense for my values of A and B to be?
0 and 4.
0 and 4. So integrating from 0 to 4. So our radius, what's our radius going to come from here?
F of x.
F of x. So in our case, I didn't really give it to you, but what is f of x equal to? It's just 4. Yeah, in this case, it's a constant. So pi times 4 squared, and then the height of the cylinder is always going to be just whatever the dx thickness is, a differential term. So if we clean this up a little bit, and haven't done this yet, but you can absolutely just pull the pi out. So here's our very simple integral we're gonna compute. So obviously computing this integral is not going to be a big deal. Setting it up is almost always going to be where the difficulty comes from. So very simple example here, but this is not something we've seen before. So if you have any questions, please, yeah, go ahead and stop me. How do we feel about where we are right now? And just a reminder, if you want to, and I always encourage you to ask your questions publicly for the good of the group, but if you If you'd rather send me a private message as well, I have the chat open. All right, so from here, let's just actually take this integral. Antiderivative of a constant is really simple. So pi times 16x evaluated from 0 to 4, and I should get 64 pi. Now, does that make sense with my geometry formula here? So we said the radius is always 4. What's the height of this cylinder?
4.
Also 4. So yeah, 4 cubed is going to be 64 pi as well. So checks out both ways. Any questions on this one here? All right. So let's look at another relatively simple function here. So still want to revolve this thing around the x-axis. So still revolving or integrating from a to b of pi times radius squared height. So in this case, if I were to take a elementary vertical rectangle here, so any individual rectangle like this is going to give me a cylinder. But if I were to just take this area as a whole and revolve it around the x-axis, what shape would that give me? What three-dimensional shape would that be?
A cone.
That's going to be a cone. So again, we have if you remember it, we have a formula for that I'll leave off to the side here, but we'll use that to check ourselves again. So let's start setting up this integral. What is again, the limits are going to be 0 and 4. All right, in this case, what's our radius going to be?
Be the slope of the line.
Just the slope? So 1?
No,
No, it's x equals y. No.
Yeah, so yeah, it's remember this radius is always going to come from, you know, the value of the function itself. So yeah, there's a slope a line of slope 1, or yeah, really this is just equal to, this is f of x equals x. So are we okay with this integral here? All right, talk me through it. How do I evaluate this thing?
I would put pi on the outside.
Okay.
And then x cubed over, oh, sorry.
Oh, you're good.
But yeah, x cubed over 3 from 0 to 4.
Okay. That's going to give me pi times 64 thirds minus 0 thirds So you got 64 pi over 3. Does anyone happen to remember what that geometric formula for the volume of a cone is?
Wouldn't it
Isn't it
just be one?
Oh, you
Sorry,
can
go
go.
ahead. Isn't it just 1/3 times the volume of the cylinder?
Yeah, it's 1/3 pi r squared h. So in this case, we know our radius is 4. Height is 4, and really this is very intentionally made this very similar dimensions to our cylinder in the last example, but yeah, I'm gonna get 64 pi over 3 again. So that checks out. So both the examples are pretty simple, but I think it's good to kind of build up to the more complicated ones. How are we doing with these first two? Any questions before I go on? All right. So not going to provide a sketch this time. I'll have, I think I'm going to have one of you do it. So I want to find the volume of the solid obtained by rotating over the x-axis, that curve there. So let's try this. Let's take a minute or two to sketch that on your own, and then I'll get someone to annotate my screen and kind of start building this up. So take a minute or two, and then I'll open it back up to you soon.
It's like a parabola.
Yeah, it will be, or at least half of one.
Half of one.
Yeah.
So would it also make a cone?
No. Cone has to have a straight slanted side, right? No, this is not going to be a cone. Does anybody want to annotate my screen here? Draw me this region.
I can try, but I promise it will be very ugly.
Yeah, you've seen me draw things the last couple of days. I don't think anyone's good at drawing on the screen.
Yeah, hang on. Let me try to find the tool. Okay, wait, annotate. Draw. Not change the color at all. Wait. This is like literally my first time ever doing this.
That's what And it's just a sketch. It's really just to organize us. It doesn't have to be.
I like, and also I forget what square root x would look like as a
Okay.
function. I think it's just like one straight line going out, or like not straight line, but like one curve.
Right. So yeah, it is a curve. I think what you've actually drawn there is closer to y equals x squared.
Line. Okay.
So think about it this way. think about what happens with the square root as x gets very big. The y values are always going to be increasing, but it's going to not flatten out, but it's basically going to taper off.
So kind of like that.
But yeah, a lot like that. So I'll go ahead and take over, but that was good. So let's say this is 0 and this is 1, which means then this y value is also 1. So I'm going to take this area right here. I'll just draw one representative rectangle here. I'm going to revolve this thing around the x-axis, and this is not a cone, it's not a cylinder, this is not something we have a nice formula for. So still integrating from a to b of some pi r squared h. So I'll kind of put this on you all. So tell me what to write here. What's this integral going to look like?
It would be from 0 to 1
0 to 1.
and pi times the square root of x squared. And then dx.
Which ends up coming out real simple.
Wait, but it's a bit confusing.
What's that?
I'm trying to understand, like, because no, it's not confusing. Like, without the units, it's sort of like hard. I don't know.
Without the units, it's what? I'm sorry, I didn't catch that.
Okay, without the units, like, I don't know. It just seems intuitively hard. Like this, we sort of like feel like that square root of x is like,
Sure.
and
Here's what I think you're getting hung up on, because I think we're used to seeing, all right, that's x, and it's x to the first power. So that means I'm just dealing with a one-dimensional length. Let's give this units here. Let's say that all these lengths are going to be measured in meters. So this right here is f of x equals square root of x. And if that's the case, then what's f of x measured in? Let's actually give a value here. Let's say x is equal to 1/2. So x is equal to 0.5. Then that would mean that f of x is going to be equal to the square root of 0.5 meters. Or I think that if this is just memory, so if I'm wrong, catch me. I think that's about 0.707 meters. So that's that f of x. Our radius for this particular value of x is going to be 0.707 meters. So from there, how would I find, like, what happens to this if I were to square it? So 0.707 meters squared. So not only do I square this, this coefficient, this numerical coefficient, so that would be 0.5. But now I also have to square that unit as well. So this comes out to be 0.5 meters squared. So I hope that's what you were asking me about. But yeah, I mean, I think it's kind of difficult when, you know, when we're doing calculations like this in math, we typically kind of relax on carrying the units around. But in this case, yeah, we're still respecting the units. We're still going to get a three-dimensional measurement. So this basically, yeah, radical x is going to be, you know, as we showed here, that's going to be a length in one dimension. Squaring it is going to give us our second dimension, and then multiplying it by dx is going to give us that third dimension.
Got it.
All right, anything else before we finish computing this? Right, does anybody have a final volume for me?
I got pi over 2.
Pi over 2? Sounds good. Let's just, for the good of the notes, let's make sure we have that. So it's going to be 1/2 pi x squared from 1 to 0. And yeah, indeed. All right, any questions on this one? All right, so I want to find the volume of the solid obtained by rotating over the y-axis this region. So bounded by y equals x cubed, y equals 8, and x equals 0. So here's what I'd like y'all to do first. Go ahead and sketch this out. This is just a good habit to get into. I think with the volumes, I'll tell you the temptation I've seen in other students before, and the one I still remember, the shortcut I still remember trying to take when I was first learning, you know, volumes of solids of revolution is, you know what? I know that I know this is the way to find the volume. So I'm just going to start filling in all that stuff. I'll do the integral and then I'll be done. It really, really pays to kind of look at what the region looks like that you're going to be revolving around your axis. So try to get a sense of that first before we actually go through with this. So take a couple of minutes and then we'll get going from there. All right, so hopefully your sketch looks something like mine. So y equals x cubed is this this curve. Y equals 8 horizontal line. X equals 0 is the y-axis. Now I want to revolve this thing, this region. I want to revolve it around the y-axis. So what does that mean for me? So for this integral we're about to set up, since I want to revolve this around the y-axis, what does that mean for my integral?
You want it in terms of y?
One in terms of y, right? So if I want it in terms of y, let's just really make this explicit first. I want my limits of integration to be in terms of y. I want my, so before I go any further, actually, let's do a, if y is my independent variable, then I'm going to have rectangles that look like this. It's going to be a dy. Actually, I'll label that on the outside, because if I revolve this around the y-axis, so that is still a cylinder, but now it's standing straight up as opposed to the ones that are lying on their side, kind of on all the previous examples. So what does it make sense for our limits of integration to be? What are our lower and upper bounds going to be for y?
Zero and 8.
Going to be 0 and 8. All right, now let's deal with the radius. So maybe I'll draw one more region in here near the bottom.
Oh wait, Professor.
Yeah.
Like I have a doubt. When you sort of like look at it, it shouldn't it sort of like be 8 to 0, because it's like the height is sort of like decreasing, right?
It's decreasing, right? But think about the order we usually take when we deal with integrals.
Okay.
We usually go, yeah, with from lesser value to greater value. You absolutely can set this up from 8 to 0. I think you're going to get a negative number, which you can, yeah, you'll realize you'll just need to take the opposite of, but you should still get the same number. All right, so back to the radius. So what's going to define the radius for, either one of these two strips I drew, or anywhere else I could draw one? Let me ask you this way. I don't think I've mentioned it like this. Is the radius going to be a horizontal measurement or a vertical measurement for this example?
Horizontal.
It's going to be a horizontal measurement, right? So it's going to be something in the x direction. And in this case, I think it's going to simply be the x value, right? I'll leave this h for a second. Actually, you know what? Let's take care of the h. What's the h going to be for this integral?
Would it be y
Not
Oh, wait,
y.
or dy?
Professor, I have a doubt. Is it x or x cube? I don't know.
No, it's going to be x squared, and here's why. So let me start off by saying this. This integral is not ready for us to deal with. I'm kind of just building it up in pieces. But if you look at this diagram over here, basically, if we're looking at our radius, so our axis of rotation is the y-axis. Our distance from that axis to the curve is really just going to be whatever the x value is. So this is an x value. This is an x value. And even though we didn't state this for the other examples, let me go back a couple of slides just to make this clear. This looks weird without your drawing, Alistair. This right here, let me go ahead and put a step in here that we didn't have before. But really what we're looking at is the volume is going to be the integral from 0 to 1 of pi y squared dx. Because that radius really does come from, you know, f of x or y. That radius comes from the height of the function. But of course, you can't leave it like this. You have to, in order for us to deal with an integral, we have to have all the variables be alike. So yeah, didn't really use this as a as an intermediate step, but it's a good analogy for what we're doing now. So now what I have to do is my last, or not my last, but my next step here is I got to express this x in terms of y. So how would I express x in terms of y? Because really x is going to be a function of y, which is, you know, the opposite of how I think you're used to looking at that. But that's our situation. How can I express x in terms of y?
Take the inverse of the function.
Yep. So really, this curve is defined by y equals x cubed. So if y equals x cubed, that means that x equals y to the 1/3 or.
Oh, so sorry to interrupt. So the
Oh,
other
no.
one you were rotating around the y-axis, and this one is like around the x-axis. So the x becomes the radius.
I think you said it's the other way around. Every other example we've done, we've
Oh.
been revolving around the x-axis.
Yeah,
This
And
one's
this one is
revolving
a-
around the y.
y-axis. Okay. Yeah.
Yeah, and so, and for this disk method, basically whatever line you're revolving around is going to dictate what your independent variable is. So we're doing the y-axis. We want y to be the independent variable. So this right here was, you know, the next piece in the puzzle. Strange. But now I can drop that in for my x. So I'll just leave it as y to the 1/3 squared dy. I think that's a good place to stop and make sure we're all okay with it. Any questions about how we got here? And are we okay with the differences from revolving around the x-axis to revolving around the y-axis? All right, so let's go ahead and keep computing here. So integral from 0 to 8 of pi times y to the 2/3 dy. All right, what's the integral of y to the 2/3?
Um, 3y to the 5/3 over 5.
And I think 8 to the 5/3 comes out to be 32. So I believe this comes out to be 96 pi over 5.
I have a question.
Go ahead, Colin.
So when we changed the x to the y to the 1/3,
Mhm.
is that because the x value was where the x to the third like is? You know what I mean? Like it stops at that line.
I think I understand what you're saying. Yeah, basically the bottom line is that the radius. So, and I'm gonna I'll probably repeat this a few more times when we're talking about volume, but remember the most basic definition for a radius is the distance from the center of a circle to the circumference of that circle. So, no matter where, I'll try to squeeze one more circle in here. But if I were to draw a circle there, then the distance from this axis of rotation to the curve itself, that right there is going to be given by the x value of that curve, which is the same as saying f of y. So yeah, the radius in this example is going to come from whatever the x value of that function is, whatever the x value of that curve is. So radius comes from the x value, but we have to write this whole integral in terms of the variable y. So that means we have to translate that x in terms of y so we can actually complete the integral. Did I answer what you were asking, or were you after something different, Colin?
No, that makes sense now.
Okay, good question. Anything else about this one? All right. So I have we're just coming up on our first hour here. Are people doing okay, or should we take a break, or do we want to just power through a little longer?
I vote for powering through for another 30 minutes and then taking a break halfway.
Okay. All right. So yeah, let's at least do this one more method, or one more example from our next method here. As you've probably noticed, you're not seeing the word disk up here anymore. So why is that? So now I'm going to involve a couple of different curves here. So I want to take this region R, which is enclosed by these two curves, y equals x cubed. And we're going to find the volume when I revolve that around the x-axis. So same as before, I'm going to pause for a couple minutes here to have you kind of sketch out this region. This one's going to be a little different. So everything we've done so far, the region that we're revolving has actually, has been flush against the axis rotation. We're not going to be seeing that anymore. So go ahead and sketch this out. Just want to make sure you're kind of visualizing the right things right. And then we'll check back in a couple minutes.
I think I know why they call it washer.
Yeah, yeah, if you're sketching this correctly, it should become pretty clear why it's washer instead of disc this time. All right, let's start drawing this thing out. And kind of focus on the first quadrant. All right, so hopefully your sketch looks quite a bit like mine. So we're revolving around the x-axis. You're going to see a lot of similarities between the way we handle the previous ones and this one. But the big glaring difference, like I said, is that, you know, if I were to draw a typical rectangle, and then wrap this around, so this is why no one should be apologizing to me for their drawings. This is so bad, but that's okay. So I've kind of drawn half of what this shape is going to be. But if I were to take a rectangle like the one I shaded in and revolve it around the x-axis, who can describe what type of three-dimensional object I'm constructing there?
Or washer.
A washer. Let's stick with the geometric terms here. Is there is there a technical geometric definition that I'm following there? And I'll try to recreate this on the side here.
Well, you would, I'm forgetting the exact definition, but you would take you would subtract the inner cylinder from the outer cylinder. Sorry.
Right. So we don't technically have a single cylinder anymore. What we have is this. If you were to look at it head on, like I've kind of drawn you the cross section over here, it's going to look like a donut. I'm going to have a cylinder that has a smaller cylinder drilled through the center of it. And that's the kind of shape we're going to be dealing with here. So let's say hypothetically, we have an outer radius, like an outer radius and an inner radius of this cylinder I've drawn over here. Let's say this outer radius is going to be 6, and this inner radius is going to be 2. And for our intents and purposes, let's just treat this as a circle. How would I find the area of this shape here? Which, if anyone cares, this is called an annulus. A circle with another circle removed from the center. How would I find the area of this annulus here?
You'd subtract the big area from the little area.
Okay, so let me try to.
Isn't it just the area of the smaller? I don't.
Let me ask you this: would this be accurate if I just did pi times 6 minus 2 squared? So basically, I'm just going to take the difference between the two radii, square that, multiply by pi. Is that okay?
No.
No. So what we really have to do is find the area of the larger circle, find the area of the smaller circle, and find their difference. So using this as an analogy to build up this this integral here. So really what we've been doing is the volume of integration using the disk method was this. The volume from A to B of f of x squared dx. So how would I have to modify that for this kind of arrangement where I have multiple curves? I have multiple functions. I'm not making disks anymore. I'm making these washers that have a hole in the middle. How would I have to modify this this thing right here, which is our disk method, to be usable for what I want to do?
Would it be f of x squared minus g of x squared?
Let's take a look. And I've left off something important, which I did not mean to do. What have I left off of both of these?
Pi.
Pi.
So how do we feel about this thing right here?
Would it instead be just f of x minus g of x and that whole thing squared instead?
So,
That kind of just the same thing.
and that I'm glad that came up, because this is why I did these two examples over here. So remember this one right here? I tried to basically keep in mind that F and G are going to give you your inner and outer radii for each individual cylinder you make. Just like here for this annulus, 6 was the outer radius, 2 was the inner radius. And a few of you decided that it would not be correct for me to just subtract 6 minus 2 and call that my single radius. So that's the same kind of idea. I can use this, but this is a very different thing from this. So this thing right here is not going to get us to where we want to go. And I'm going to go ahead and write this one more way just to really kind of drive home what we're doing. And I think somebody said this, or maybe it was in relation to just circles, but really what we're doing here is we're finding the volume of a large cylinder, finding the volume of a small cylinder, and finding the difference between them. So I'm going to write this one more time like this. The integral from A to B of pi f of x squared dx minus a separate integral And are we okay with the notion that these two things right here are equivalent?
Yeah.
Yes.
So I really and kind of think about when we were doing areas between curves yesterday. The first example we did, we treated it as two integrals. But really you can get away with just doing one if you're careful about how you handle the individual functions. For this example, let's, at least at the beginning, let's set it up from here. So for this volume, first of all, what are our limits of integration going to be?
Zero to one.
0 to 1. All right, so just like with the area between curves, I need to figure out what my outer function is and what my inner function is. So in this case, we've called my outer function f. What's my outer function? Where's my outer radius going to come from in this example?
So y equals x.
Y equals x. Yeah, the straight line is above the curve. So this one's going to be x squared dx. Same limits of integration. But this one's going to be x cubed squared dx. Any questions with that setup there? Right, let's clean it up a little bit. And I believe that's going to come out to be pi over 3 minus pi over 7. Which should be 4 pi over 21. Please check me. Any questions on the way we approached that or set that up or anything really?
The only real problem I have here is just like visualizing the washer.
Right.
Like every time I like do the little initial sketch, I always make a cylinder. But I guess that's just practice.
Okay. So in response to that, let's go ahead and start over here. Let's get rid of some of this stuff. We don't want to get rid of that axis. Wow. That's better. Okay. So here's my full area that I want to revolve around the x-axis. So first of all, are we okay with this being a kind of a representative rectangle for this region? So now that I've drawn that rectangle, what is it about this rectangle, the way I've drawn it, that should suggest that I'm going to use the washer method to find this volume and not the disk method? Another way I'll try to word or try to ask this a different way. What's the difference between this example and all the other ones we've done so far?
It doesn't touch the axis of rotation.
Yeah, it does not. So it does not contact the axis we're looking at. So I'm going to try to redraw this washer, even though I admit it's difficult. So, in every other example, we've kind of had to basically, once you get this rectangle drawn, I'll start with the upper edge because that's not unique to this example. So basically, I'm going to try to revolve this upper edge around the x-axis like that. Gives me this here. And, you know, with all those disk method examples, since my region does contact the axis of rotation, I am just able to, I can get away with that and just kind of fill the whole thing in. But now I have to respect the fact that this lower edge of this rectangle does not contact the x-axis. So I'm going to give it its own little sweep like this and then contact them here. But I think it's really important and really a good thing to pause on here is, you know, how do we know when we use the disk method and how do we know when we use the washer method? And it really, I can't remember who answered this, but they were dead on. What we're looking at is, the question we have to answer is, does the region we're revolving around the axis of rotation, does that region contact the axis of rotation? If it does, you're looking at disk method. If it does not, you're looking at washer method. Any more questions on this one before we move to our next slide? All right. So very glad I put this in now because hopefully this is going to be
My internet cut out.
that's okay. So Alistair, I think this is hopefully this is what you're after. This is a much better graphical representation of what the washer method is doing. So in this case, you know, our region that we're going to revolve around the x-axis, it does not come in contact with the x-axis. So these cylinders we're making, and remember, when the way we're going to handle volume, it's always going to be, you know, an aggregate, an accumulation of these little cylinders. These cylinders are, however, going to be hollow. If I wrap this rectangle around the x-axis, you're going to get this, you're going to get all these different washers, all these different, basically cylinders that have another cylinder removed from them. And I'll just go ahead and recreate it here, but they're calling upper function F. So really what we have here is, I keep forgetting this little pi. So any questions between on the difference between disk and washer so far? One thing I would really try to focus on from your point of view is, do you know what to look for in order to make that determination if you're looking at whether to do disk method or washer method? Basically, the sooner you can make that determination, the better off you'll be. So any more questions before I move on from this this diagram here? Actually, you know what? We're at a pretty good stopping point. Let's go ahead and do this. I have 732. Let's all come back at 7:42. Sound good?
Yeah.
I will see you all then.
Steven, my internet keeps cutting out.
Okay.
So if I disappear, it's
All right. I understand. All right, I hope I have everyone back now. So sticking with the washer method, we're gonna look at an example now where the axis we're dealing with is not going to be the X or Y axis. So actually dealing with the same region as before. So the sketch is gonna start off looking familiar. All right, so if we were just worried about the area, this region is the exact same region as the one we just looked at. But now we're going to be revolving this around a different axis of rotation. So we're going to have our volume is going to be different. Our integral is going to be set out different. So let's just start with washer method. So our volume is going to be something of this form. The integral from a to b of outer function squared minus inner function squared dx. So now, first thing to consider here is if we're going to be revolving around the axis or the line y equals 2, what is the outer function going to be this time? So if I take a strip like this, and again, just think about what radius means. Radius is the distance from the center of a circle. In that case, that would be up here. The distance from the center of a circle to that circumference. So which one of these things is going to be further away? Is it going to be the curve or is it going to be the line?
The curve.
Going to be the curve this time. So in this case, I will call f of x equal to x cubed and g of x equal to x. All right, so now we need to figure out, and I'm going to go ahead and rewrite this one more time. So I'm going to go ahead and just put the limits of integration in as 0, 1. We're still looking at that x interval. We're still using x as our independent variable. But now I'm going to write this as this. Capital R x of x squared minus lowercase r of x squared. So outer radius and inner radius. So let's just handle these one at a time. And I'll draw a couple, or yeah, let's draw one, at least one more representative rectangle here.
What
is
is
the-
the question?
Yeah, go ahead, Colin.
Are you forgetting the pi in the equation, or is there not a pi? in
Yeah,
the
I keep forgetting it. No, it absolutely should be there. Thank you. All right. So let's talk about the outer radius first. And basically, that's going to be the distance from this line this horizontal line y equals 2 to the curve. So let's just do it like this for now. I want an expression for r of x, capital of r of x, and I want an expression for lowercase r of x. So for any x value, how could I get that upper radius, that capital R? Maybe let's look at a specific example. Let's say x equals 0.3. How would I find the outer radius when x is equal to 0.3? Walk me through how I would calculate that.
Would you plug x in or 0.3 into f of x?
Okay, let's start there. So we have f of x is going to be equal to 0.3 cubed. That'll be equal to 0.27. No. .027, I believe. Okay. So that's a
And then
start.
Would you subtract 2 from it? Or-
Subtract 2 from it. I think you mean subtract that
two.
from 2.
Yeah, that's what I meant.
All right, let's put it to the rest of the group here. What do we think about that method there? So for any given x value, I'm going to cube it. Then I'm going to subtract that cube from 2. Any protest there? You feel okay about it? Okay, that's totally solid. So if we generalize that, then what we're going to have is this. Okay, so we have 2 minus x cubed. How about for the inner radius? What would that expression look like? What would lowercase r of x look like?
Two minus x.
It'd be 2 minus x. All right, so now that we have these, let's go ahead and continue to the integral. So we're gonna have 2 minus x cubed squared minus 2 minus x squared dx. So let's go ahead and stop there for just a bit. So this is kind of a different scenario than the ones we've been doing. Now that we're dealing with an axis of rotation that's removed from our 2 coordinate axes. Any questions about how we set this up? Right. In that case, we'll go ahead and finish computing here. Gonna do some expanding first. So 4 minus 4x cubed. gonna go ahead and pause there because I feel like I made a mistake even though I can't find it.
Is it supposed to be positive x to the sixth when you expand or like?
Absolutely is. Yep. So where did that mess me up? Yeah, good catch on that. I think that was it. All right, any questions here? All right, let's go ahead and go again. All right, so we're gonna hit the same region one more time, except now we're gonna revolve this around x equals 1. So if we're gonna revolve around x equals 1, what implications does that have for my my integral? What's gonna be the difference in how I set this up?
Would it be for variables in y?
Yep. And what tells you that, Jacob? How do you know that the independent variable is gonna be y?
Because you're rotating around a vertical line.
Yep, absolutely. So we're rotating it around something that's parallel to the y-axis, so we need to be using y as our independent variable. And we're going to be going around this axis, x equals 1. All right, and I'll just, like we've agreed upon, we need to use y as our independent variable, which means all of our intervals are going to be delta y intervals. So I'll draw a couple of representative rectangles in here. Okay. All right, and I'll let you all drive for a bit. What do we need to do next?
Find the big and small radius.
Right, so we need to find expressions for capital R sub of y and lowercase r of y. So where are we going to get our outer radius from? Is that going to come from the line or from the curve in this case?
The line.
It's going to come from the line. How do you know that, Colin?
Because it's the farthest away from the axis of rotation.
That's exactly it. So yeah, our axis of rotation is at x equals 1. So we want to deal with our line here. So we know that this is going to involve this equation, y equals x. It's not going to be equal to y, but it's going to be a function of that. So then now what we need is an expression for r of y. So for any given y value, how would I get that radius?
Would it be 1 minus y?
Okay, I got to vote for 1 minus y. Let's see what we think. Anybody have anything different, or do we like 1 minus y? What do we think? So one way to look at things like this is, you're trying to find, essentially, for this example, you're trying to find that length. So, and remember, like I've said a few times now, the radius is really going to be the distance from this axis to the line. And we know that axis is x equals 1. This line is x equals y. So it stands to reason that that difference is going to be basically x maximum minus x minimum. In fact, I'll even write that. X max minus x min, which is going to be 1 minus y. All right, now same drill for the inner radius. Again, going to be x max I guess I should be saying this like, no, that's fine. In this case, the x max is still 1. But now for the inner radius, what is my x min going to be?
Y to the 1/3.
How'd you get y to the 1/3?
I took the cube root of both sides from the y equals x to the 3rd.
So yeah, we're just remember everything when we do this integral, let's go all of the independent variables have to be y. So yeah, our x min here is going to come from this curve. So I want it to be inverted. So now we can start setting up the integral, or really finish setting it up. We've done most of the hard work. What are the limits of integration going to be?
Zero to 1.
Still 0 to 1. And that's just a coincidence. It's the x limits happen to be the same as the y limits. I want to do 1 minus y squared minus 1 minus y to the 1/3 squared dy. All right, has anybody gotten a final volume for this one yet? Running out of room. So I trust that you all can add those common denominator or find a common denominator and add those fractions together. But let's focus on the calculus of this example here. Any questions about how we set this up? I think probably the trickiest parts here are finding these expressions for the outer radius and the inner radius. So if there are any questions there, those would be definitely worth talking about. Any questions about this at all? Okay, let's go ahead and keep going. All right, we got a new situation here. I'll go ahead and put this back to you. So take a couple of minutes here and you know what, I'll give you a little longer because I want to basically go as far as you can with this one. So let me give you like 5 minutes at least to get started here. If you have any questions, please either put it in chat or just speak up. But yeah, we've been doing volumes for a little bit now, so let's see how deep into this you can get without without me. So I got 8:10. I'll check back in with you around 8:15, and I'll get some guidance from you. All right, I have 8:16 here. We still want a minute, or we okay to talk about this? So I see you have some annotations here. So x equals 0 is going to be the y-axis. Y equals 1 should be that red horizontal line there. X equals 1 is that yellow vertical line. The last thing we need is this this parabola here, y equals x minus 1 squared plus 1. And I am not sure that's where that's going to be. This is where I think that parabola is going to be.
Sorry, my bad. I just
No, you're okay.
have a bad
No, you're
drawing.
okay. And now that I'm seeing this, I don't see how this example is going to work.
How are you gonna like, I don't know, like, what?
So the axis of rotation is going to be down here, right? This is going to be y equals -1. So next thing we do, let's shade in the region that we're talking about here. So this parabola is going to hit the, it's going to intersect the, oh yeah, this will work. This parabola is going to intersect the y-axis at some point, right? So I believe the region we're talking about is going to be in here. Really, it's going to continue upward quite a bit.
So it's just gonna be the equation of the parabola minus the y, sorry, -1 minus the parabola and then pi.
Let's see. So let's start with our, let me ask this question first. And I think most of you have probably already thought about this, but what is our independent variable going to be?
X.
It's going to be x, right? Now, how do we know that?
Because it's rotated to something parallel to the x-axis.
Absolutely, that's it. So yeah, we're going over a horizontal line. So just like before, we're going to want to deal with our outer radius and our inner radius. So in this case, what is our outer radius going to be? Is that going to come from the parabola, or is that going to come from something else?
The parabola.
It's going to come from the parabola, right? So at this point, let's draw a rectangle to help us here. So basically what we're looking at is this. I want this distance here from the outer edge of that parabola to the axis of rotation. So how am I going to find that distance? That distance is going to give me my capital R of X. Does anybody have an expression for that yet?
Would it be that function plus 1?
When you say that function, which one do you mean?
The x minus 1 squared plus 1.
Yeah, it would be, and I'm gonna go ahead and write it like this for now to explain why. So here's your basically x minus 1 squared plus 1. That's gonna give you the outer boundary here, and then we're subtracting from that -1. Because basically you're 1 more unit away from that because my axis of rotation is further away. It's below the x-axis. So re-express this and simplify x minus 1 squared plus 2. But yes, I agree with that. What is the inner radius going to be?
Two.
It's just going to be simply 2. So what's nice about this one is that the inner radius is just it's a horizontal line. So that's going to be just basically, this is y equals 1. So the difference between y equals 1 and y equals -1 is just 2. So from there, I can start setting up this integral. What are my limits going to be?
Zero and 1.
Yep, 0 to 1. And I'm looking at
Wasn't the x minus 1 from the equation like right above supposed to be squared inside the parentheses too?
yes, it is. Good catch. So that means to the 4th squared. I think I'm okay now, but give me another sanity check if you could.
Can we just say x minus 1 equals u or something? Is that possible?
Yeah, I was hoping somebody would bring that up. I think from here, that's a good suggestion. Because I would really like to avoid expanding that. So yeah, that's a good idea. Let's do this. If u is equal to x minus 1. Actually, you all tell me. What consequences follow from u being equal to 1?
Du equals dx.
Du equals dx, that's good. I think there are other consequences we need to worry about.
We need to change the bounds.
Yep, the bounds are going to change as well. What are they going to change to?
-1 and 0.
-1 and 0. Okay, so now we're going to get a new integral. So pi, and then we're going to go from -1 to 0. And since dx equals du, this should just be pretty straightforward. U to the 4th plus 4u squared u.
Minus 2 by 15. Minus 2 by 15.
I'm sorry, what was that?
Minus 2 by 15 pi. No.
Okay.
8 by 15 pi.
Okay. Eight pi over 15. Actually, I think it should be bigger than that.
23 over 15 pi.
Yeah, that's what I'm seeing. Rios, I think you have a sign flip somewhere. Yeah, I agree with 23 pi over 15.
Oh, got it. Wait, Professor.
Yes.
You cross multiply. I just don't understand. Like, how do you? There's just no way.
What?
Oh, it's a 4
what?
by 3. Okay, it's a 4 by 3. Okay,
Yeah.
I made a mistake.
Oh, okay. So you're understanding this this step right here?
Yes.
Okay. Right. Any other questions about this one? I think I have one more example tonight. All right, let's go ahead and finish up. All right, so I intended this last example. I broke this last example up into 3 parts here. Actually, let's go ahead and go through it. I think the whole thing is going to be at least the first 2 parts. So first thing is going to be area here. So how am I going to deal with the area bounded by these 2 curves?
Should I draw the graph?
Yeah, let's take a look at the graph. And actually, there's something I might be able to do to, oh, go ahead. No, that's what you meant. Yeah, you go for it. But there's something we might be able to do in advance that would help us with this graph.
And find the bounds.
Yeah, find the bounds. So yeah, the bounds are going to come from where these graphs intersect. So let's do that. So 4 radical x equals x plus 3. I'll go ahead and square both sides. So I'll get 16x equals x plus 3 squared. And I believe that factors like this: x minus 1, x minus 9 equals 0. So our bounds are going to be x equals 1 and 9. So Riaz, is your straight line graph on the right of those two?
Yeah, it's just happening. Yeah.
So it looks
Should
like
I
you have
erase it? I think there might be an error.
yeah, there is. I'll go ahead and take over there. And I think for the line at least you had an x-intercept of 3, but really it should be a y-intercept of 3.
Yeah, yeah.
We know that at x equals 1 and x equals 9, we're going to have, so this is going to be really rough, but I think that's okay. It's really, I just want to help organize. So that's x equals 1, x equals 9. All right. So here's our region. And I want to find the area of that region. So got the bounds. So what's the rest of this integral going to look like?
Isn't it just top minus bottom and dx and integrate everything?
So I'll call that, actually, I'll write it in English here. So upper, what is that? I don't like it.
Big greater.
Yeah, we'll just
uh,
stop at pen. All right. Greater minus lesser dx. So in this case, what is the greater function? Is it this square root function or the linear function?
The square root function.
It'll be the square root function. Which means the lesser function is x plus 3. All right, so, and we start integrating. So 4x to the 3 halves over 3 halves minus 1/2 x squared minus 3x And if anybody has a final answer here, go ahead and shout it out. I'm just verifying what I have. But I believe this is the final area, 16/3. Right, any questions on this area here? Obviously, hopefully that was a good review for the stuff we did yesterday. Right, I think these next two parts are volumes, but let's see what the differences are. So volume revolved around the y-axis and volume revolved around x equals 9. Let's just do one of these parts. Let's go ahead and just do this one. So I'll go ahead and draw that region again. All right, so same region as before. Now we're going to take this area, revolve it around this line x equals 9 to make a solid, and we want to find that volume. So I'll let you all drive. What should I do to start setting this up?
Create the equation for the bigger radius and the smaller radius.
So we want to find capital R and lowercase r. What's our independent variable going to be?
Y.
Going to be y. And once again, what tells you that?
It's parallel with y-axis.
Parallel to the y-axis. Good. All right, so I'm going to draw a rectangle in this region here. Should I draw it vertically or horizontally?
Horizontal.
So remember, and that all comes from, that's a direct result of whatever our independent variable is. So since I'm using y as my independent variable, then this interval right here is going to be a delta y interval. So that thickness is going to be something vertical. All right, so we want to make expressions for the outer radius and the inner radius. Who has an idea for an expression for the outer radius here?
Would it be 9 minus 4 square root x?
9 minus 4 radical x. So you are saying that the outer radius comes from the parabola, the curve. We okay with that? Good. All right, so 9 minus 4 radical x, are we okay with that?
But it has to be in terms of y.
Yep, so you chose the right function, but yeah, we got to translate that in terms of y. So really, for right now, I'm gonna leave this like this, 9 minus x. So basically what we have to do is swap out that x for a function that's in terms of y. So how would I get that function?
Y by 16.
What was that? Y over 16?
Yeah.
I think there's something you might have missed there.
Y squared over 16. Sorry.
Y squared, yeah, y squared over 16. And just for the good of the group, where did that come from?
Oh, you have the first equation, y equals 4 square root of x. You divide it throughout by 4 and then take the square.
Y over 4 equals radical x. And then from there, y over 4 squared equals x. And that's what we have there. So we got a good expression for the outer radius. Now, how about the inner radius?
Be 6 minus y.
6 minus y. How'd you get that?
From changing the x plus 3 equation to y, it'd be y minus 3. And I just subtracted the 9 and 3 together to get the 6.
So let's do that a little more slowly. So 9 minus x, or 9 minus y minus 3. And I think you might have had a bit of a sign issue there.
Oh,
I
12.
mean,
Oh,
12
yeah.
minus y. So yeah, just be careful, take it as slow as you need to, but yeah, I mean, sign flips are always dangerous. All right, so we got good expressions now for capital R and so the outer radius and inner radius. Now what can we do?
Put them into the volume equation.
Okay, and tell me what that integral is going to look like.
It'd be pi, then the integral of between 0 and 9. And then 9 minus y squared over 16. And that whole thing squared. Minus the 12 minus y squared. And dy.
All right, how do we feel about this? I think I have an issue with the limits. So we found, I think we found that this thing, these two equations intersect at x equals 1 and 9 earlier, right? Someone check me on that, but I think that's what I remember.
Yeah.
So does that mean these limits should be 1 and 9?
I thought the limits were supposed to like correspond with the y-axis.
Yes, that's true. So yeah, 1 and 9 are x values, but this whole integral needs to be in the language of y. So what should my limits be instead? 4 and 12. And Mona Lisa, how did you get those new limits?
When you plug in the x into like the original, so like for either of them, since they intersect at the same place,
Mhm.
you do 1 + 3 would be 4, and then 9 + 2 would be 12.
And that's exactly it. So yeah, this integral now should be perfect. Any questions about, before we go any further, any questions for how we got here? All right, let's start computing. And I think that's as much as you can simplify it before you actually integrate it. Right, I'm actually going to ahead and stop this example here. I mean, really the new thing that we've been doing today is, setting up these integrals to find volume. Actually evaluating the integrals is something we've been doing for a while. So right now by my clock, it's 8:52. I will stay on till 9:10 if anybody wants to ask me any questions about what we did today, finish this example here. If you want to stay online and start the quiz, which should have been published just a little bit ago. Or if you'd rather go and handle all those things on your own time, that's fine too. But I'm going to go ahead and adjourn us now. And I'll see you all tomorrow unless you want to stay around and talk about something.
All right. Thank you so much, Professor.
Thank you.
Thank you.
Thank you, of course.
Thank you, Professor.
Thank you.